All right, so the second session here for Chapter 8, the basics of chemical bonding. If you recall, we had left off with making electron configurations for ions and using that to kind of give some insight into the octet rule. We got to transition metals, and that's kind of where we paused. So first, we'll look at the electrons that are lost from the outermost s orbital. So in other words, we'll lose electrons from highest n first, then from L. So let's take iron. Iron's electron configuration is argon 3d6 4s1. Okay, so here Fe2 plus is going to lose 2 electrons, and we're going to lose them both from the 4s because it's got the higher n value. Okay, then we would start to take electrons away from the L. In this case, once we got rid of those first two, we look at Fe3 plus, and now it's willing to lose a d electron. Now we pick up a little bit of stability here. So Fe3 plus is actually more stable than 2 plus. And if you recall, that's because of that half-filled energy level. So rather than having 3d6, we can drop down to 3d5. Now, what are some consequences? An M2 plus is a common oxidation state as 2 electrons are removed from the outer NS shell, right? Ions of larger charge result from loss of d electrons. So the first two are going to come from that s, the 4s in this case, and then we're going to start to lose electrons from the d. Now for your post-transition elements, in other words, take a look at tin. Tin would be krypton, and then 4d10, 5s2, 5p2. Now we know that we can form a 2 plus ion, and that means we're going to pull 2 out of the p. So the 5p is gone now. We have the 5s2 left. Now, neither has noble gas electron configuration, all right? And then, of course, if I empty the 5p, then I make a plus 4, but now I have an empty 5s subshell. So even though it's not making a noble gas, it does complete the 4th energy level and leave the 5 energy level completely empty. So that is somewhat desirable. Transition metals, not easy to predict which ions form which are stable, but ions exactly filled or half-filled d subshells are extra stable and therefore tend to form. So in other words, a manganese 2 plus would give us argon 3d5. Iron 3 plus gives us that argon 3d5. Zinc, its only one is a plus 2, and we can see it ends up with a 3d10, so it has that full d subshell. Now, predicting cation configurations then, consider bismuth, whose alpha-bal configuration would be 6s2, 4f14, 5d10, 6p3. And of course, the question becomes, what ions would you expect? The first thing we're going to do is rewrite this. So we're going to put it in order of level, right? So of n values. So we have xe, and then we have the 4, then we have the 5, then the 6s and the 6p. Now you can imagine that the plus 3 and the plus 5 would exist because we can get rid of the 6p3 and the 6s2. All right. Consider iron, whose alpha-bal configuration is 4s2 3d6. What ions are expected? Again, if you rewrite the configuration, it makes sense. Fe2 plus and Fe3 plus. All right. What about the anions? Nonmetals gain electrons to become isoelectric, electronic with next larger noble gas. So in other words, oxygen then is helium 4s2 2p4 plus how many electrons, and what would that equal? And of course, if we gain 2 electrons, then we end up with s2 2p6, so s2 p6 formation. How about nitrogen? So again, nitrogen, we know we want to probably gain 3 electrons, right? That way, again, we end up with an s2 p6 formation. All right, so let's see if you figured this out. What are the correct electron configurations for copper and copper 2 plus? So copper and copper 2 plus. So we know that we're in the 4th energy level, if you will. It's a 3D. Pull out our periodic table here. Let's turn it that way. So we know we have a 4s2, 3d9. Right, so for our ground state, we know we should have 4s2. There's a 4s2, not a 4s2, not a 4s2, 4s2, 4s2. 3d9, 3d9, 3d9. Oh, but that's potassium. So the potassium makes it wrong. All right, so we're down to 2. Okay, now what about the 2 plus? Well, what 2 electrons will we lose? All right, if I take away the 2s, then I end up with a 3d9. That makes sense. Here, it looks like we took one of the electrons and simply moved it over and gave it a 3d10 4s1 configuration. Now we know this is what it does when it shifts, but not as a +2, right? So let's see. Now we got rid of this one, but look, it did that shift. So it's not a 4s2, that's the shift right there. And then what 2 electrons will we lose? Well, 1 and 2. So maybe you were smarter than me and you had C right from the get-go. Hopefully you did. Good job. Filled and half-filled orbitals, again, remember, were completely stable. So you might remember copper was an exception for us, right? Chromium was the same way. It's copper and chromium. They each move 1 electron out of the S, put it into the D to make either a half or a full D. And then, of course, that was actually the basis we had to start with, right? So maybe I threw you off when I said that. I don't know. All right, what are the correct electron configurations for zirconium-2 and zirconium-4 ions? So zirconium-2, so Zr, which means we're going to go down to the 5th period. We're going to go through 5s2, and then we're going to have 4d2. So we're going to have 5s2, 4d2. So we have 5s2, 4d2. This time there's no exceptions, right? No crazy electron movement before we look at the ground state. Okay. And in order to get there, we had to go through krypton. So anything that's not krypton, we know we can get rid of. So E and B are out, right? All right, so now we want to get to the +2 and the +4. So remember, we want to rewrite this, right, in order of N. And so it's going to be krypton, and then we'd have 4d2, 5s2. Now, which ones would I get rid of? Well, I'd get rid of the 5s2. So the +2 would look like that. And the +4 would just be the krypton. So that means it should be C. All right. So hopefully you're catching on to electron configurations and looking at transition metals and, of course, the octet rule as well with those and making ions with those. If you have questions, make sure you pop in and see me, ask in lab, or shoot me an email off to the side, something along those lines. The next topic we're going to get to is Lewis symbols, and this is usually the typical jump we make. We go from electron configurations to electron dots. So remember, this is an electron bookkeeping method. So it's basically just keeping track of the valence electrons. So we'll write the chemical symbol, and then we'll surround it by dots representing each electron. So we look at the group number, that tells us the valence numbers. All right, so group 1A has 1 valence electron. So for instance, hydrogen then would have 1 dot, lithium would have 1 dot, sodium would have 1 dot. When we get to 2A, we know that we have 2 valence electrons. Now helium has 2 dots. Notice they're not paired up. That's the only rule. Remember, we go around it as if we were going around the clock. And so we would start usually we start at the top. We'll go 1 at the top, then left, then bottom, then right. Reverse that. So top, right, bottom, left. It's just like a clock. Here, it doesn't matter as long as they're not paired up. No big deal. Okay. All right, so for the representative elements, the group number equals the number of valence electrons. So it should be pretty straightforward for the most part. All right. Now we can use a diagram electron transfer and ionic bonding. So if we look at electron dots, we know that sodium has 1 valence electron. It's going to pass that on, pass that on to the chlorine. And they don't actually show that dot. There it is. So it's a space here, right? So we're going to take this dot, we're going to move it there. That's going to give us our octet literally around the chlorine, which will become chloride. And the sodium, of course, lost one electron. Now, what we've not shown you here is, remember, this is also a full octet. We didn't discuss this as we took electrons out, but we did make a noble gas configuration. So remember, by default, that means you have met the octet rule. But don't forget, there is a layer of electrons there. They're just in one energy down. So the 3 is gone, but sodium still has a full 2 energy level. For magnesium, we'll lose 2 dots to the oxygen. That'll make Mg plus 2, O2 minus. All right, again, 1 dot. And here you can see we paired up the top. We paired up the bottom. And remember, those pairs are called lone pairs, like all alone. So L-O-N-E. Not loan as in borrowing. So it's not L-O-A-N. It's L-O-N-E. Right. Now for covalent compounds, again, from individual separate molecule, they'll form individual separate molecules. The atoms are going to be bound by sharing. Okay, so we do not conduct electricity. They typically have low melting points, and melting points is usually an indicator of bond strength. So ionic bonds typically are stronger than covalent bonds. For covalent bonds, we're going to share a pair of electrons between the atoms. So 2 hydrogen atoms will come together, and of course, a simple question would be why? So why do 2 hydrogens form the diatomic H2? So we know this is a covalent bond. That doesn't mean there's an attraction here, right? So this is still based on attractive forces. It's just not complete opposite charges. Okay, so it's not a plus and a minus. But there is still some positive and negative influence going on. Remember, the nucleus is positive. And so the nucleus is positive and will attract electrons. And so attraction of valence electrons from one atom to the nucleus of another. Okay, so we'll get a shifting of what we call the electron density. So remember those clouds we kind of formed in the last chapter where it was a probability matrix. Now what we're doing is shifting that probability around based upon the environment. So if I have 2 plus charges and I have electronic density going on here, it's now going to be pulled towards that other proton. Okay? As the distance between the nuclei will decrease, the probability of finding either electron near either nucleus will now increase. And so you can see that. So we had a probability density here, probability density there. As they come closer, this positive charge attracts that electron density. This positive charge is attracting that electron density. And then when they get close enough, we see that the electron's density can actually be somewhere in between the two as an increase. Okay? So that's what's going to pull the nuclei closer together. Now remember, the 2 nuclei themselves would repel, right? Because I have a plus charge here, a plus charge here. As we pull them together, they repel each other. But we have that nice electron density going on in between the two that's going to keep those nuclei from actually repelling each other because they're both going to be attracted to that negative center. Now for a covalent bond, as the nuclei get close, right, we can see that they'll begin to repel each other. So the bond can only get, those 2 nuclei can only get but so close to one another. They both have a high positive charge. Okay? The final internuclear distance then between the 2 atoms in a bond is the balance of attractive and repulsive forces. Bond forms since there is a net attraction. So again, they're going to come close until they do actually start to repel, and that's where they're going to stop, right? They're going to find that medium to where they can maximize that attractive force. All right, so covalent bond then, the 2 quantities characterize this bond. We'll have bond length. We just said the closer they get, the more repulsion they'll feel, right? So the distance between the 2 nuclei would be equal to the radius of A plus the radius of B. And the second thing that's going to characterize the bond is going to be the energy itself. We also refer to this as bond strength. Okay? The amount of energy released when the bond forms. Okay? So the amount of energy that must be put in to break the bond. Okay, so let's see. If I want to form the bond, right, the bond itself is going to be characterized by the length and the strength. Which species is most likely covalently bonded? So again, you can always fall back onto the basics we've learned before we got here, right? We know that metals make ionic bonds, nonmetals will make covalent bonds. So if I'm looking for a covalently bonded species, then what I'm going to do is get rid of most of my metals. So cesium would be out, sodium would be out, calcium would be out, carbon is not a metal, and magnesium would be out, which means it must be CO. What is the primary driving force behind the formation of covalent bonds? The energy released when two electrons attract each other? Well, that just makes no sense because the electrons are going to attract each other. The energy gained when two electrons, yeah, more junk. All right, let's see. The energy released when nuclei attract electrons, that's got potential. See what I did there? Potential energy, distances. Anyway, the energy released by two nuclei attracting each other, that's not going to happen. The energy gained by the repulsion between nuclei. Well, there's no energy gained by that repulsion, right? Because they're going to go back to the area where they don't repel each other anymore. So the answer here must be C. All right, what forces limit the distance between nuclei in a covalent bond? The repulsive forces between nuclei, the attractive forces between nuclei, the attractive forces between electrons, the attractive forces between nuclei and electrons, the octet rule. All right, so what force or forces limit or limits the distance between nuclei in a covalent bond? Remember, those nuclei are going to come closer and closer and closer based on the attraction to the electrons. Once they get to a certain point, the repulsion between the two is greater than the attraction of the electron, and that's what's going to limit their distance. So it must be A, the repulsive forces between the nuclei. All right, the next step is to go to Lewis structures. And so the molecular formula drawn with Lewis symbols. So we can do atomic Lewis symbols, right? I'll call those atomic dot symbols or Lewis dot symbols. The next thing we can do is Lewis dot structures. So now we're going to have covalent bonds, multiple atoms, and we're going to show how they're linked up using dots to represent those electrons. So again, for a covalent bond, we're going to have to share pairs of electrons. So each atom then will share an electron. So it has a complete octet, which means we're trying to get 8 electrons around each atom. That way they'll meet the noble gas configuration. Of course, the exception here is going to be hydrogen, which only needs to gain 1 electron to have 2 in its outermost energy level. All right, so the octet rule and covalent bonding then, when atoms form covalent bonds, they tend to share sufficient electrons so as to achieve outer shell having 8 electrons. So in other words, even though they're covalent compounds and we're going to share electrons, we're going to share them so that we can meet the octet rule. Now, we will share all of the electrons between the two atoms. So both atoms get to count both sets of electrons. That might seem a little weird, but I'm sure as we start to do some drawings, it'll make sense. We'll indicate how all atoms in the molecule are attached to one another. Okay, so we're not forming a lattice here. There's no lattice energy to be gained. The only energy we're going to get is the exothermic energy that comes off from creating the bond. Let's see, this is going to account for all valence electrons in all atoms in the molecule. And again, we'll jump into some examples and hopefully will make sense. So, each one wants to get 8 valence electrons, which means we want to fill the S and the P. So we want to have an S2P6 formation here. The stable monatomic gases, and of course, don't form compounds. So in other words, your neon, your argon, get on the list here. So helium, neon, argon, krypton, xenon, radon, none of them are going to form, anything. No, they're not going to form compounds. Of course, that's a pseudo lie. We're going to see in the next chapter some other influences for bonding and what's going to happen here. But for right now, those gases do not form compounds. All right, so Lewis structures, the diatomic gases then, we have hydrogens and halogens. H2, we're going to take 1 dot from each hydrogen, we're going to put it in the middle, and that's going to make a bond. So each hydrogen then has 2 electrons through sharing. So once we share, whatever electrons we put in the middle, both sides get to count those. Okay, we call that an overlap, and we're going to get into some details with that in the next chapter. So now, once we have that overlap, we'll draw a single line that's going to indicate that we've shared 2 electrons. Okay, so a single line is going to indicate that we've shared 2 electrons. So for F2, we can see the same thing, but notice now fluorine's bringing 7 electrons. It's got 3 lone pairs, so each one has 3 lone pairs. Draw those in real fast. Okay, so the 2 that are single are going to link up in the middle here. And of course, again, it's going to form a dash representing that single bond sharing of 2 electrons. Now, when we go to count electrons, right, we get 2, 4, 6. We get to count the one in the middle, so that's going to be 8. And then 2, 4, 6. Again, we get to count the ones in the middle for the second fluorine, so that's also going to give us 8. And so we can see that overlap right there. And that's how we're going to end up with that single bond. So each F has a complete octet this way, right? We only need to form one bond to complete that octet. Pairs of electrons not included in covalent bonds, again, are called lone pairs. Now we could do the rest of the halogens this way if we wanted. In fact, I'll ask you to do that on your own and practice and make sure you can come up with this and see how that fits together. All right, I think we'll pause here. We'll pick up with doing some more structures. And then actually, we'll go ahead and finish up. We have just a little bit left here before we get to your turn, and then we'll call it a stop there. So it's only about a minute away. Another diatomic gas would be HF. So even though it's not a diatomic in the fact that it's the same atom, it's hydrogen with another atom, right? So it's playing the same game. Just instead of having F2, now we have H and F sharing 1 electron. No big deal there. All right, so how many electrons then are required to complete the octet around nitrogen? And hopefully you came up with 3, right? And again, we'll stop it there. I told you it was only another minute. And that finishes your turn. And now we'll start to look at more complex Lewis structures and how we'll handle those and manipulate the atoms with the electrons and make sure we have complete octets.